Hi there, my name's Alex Thiedem, and this is my presentation, Java EE Revisits Design Patterns. Okay, so who am I? Well, I'm a senior Java developer who can often be found at conferences talking about various topics. More recently, I've been talking about Enterprise Edition Java. I have a blog and a Twitter account, readlearncode.com, where I publish various articles about Enterprise Edition and almost anything that I think might be interesting to an audience. So by all means, have a look. You can contact me via email, and you can also contact me on my Twitter account as well. I'm happy to hear from you. So any questions or queries, please don't hesitate to contact me. I wrote a book with my colleague Murat Yener entitled Java EE Design Patterns, and today we're going to be talking about a little bit of the sort of topics that we discussed in the actual book and trying to sort of see how Java Enterprise Edition has changed the way that design patterns are implemented. This is really the topic of the book. So if you want to buy a copy, you can do so from Amazon, and here's the QR code. Right, so what's on today? Well, basically we're going to do a very quick retrospective of design patterns. We're going to then look at how the Java Enterprise Edition programming model has changed in the recent editions of Enterprise Edition, and how that then can be used to map classical design patterns to Enterprise Edition 7. The design patterns we're going to be looking at are going to be Singleton, Factory, Façade, Decorator, and Observer. And then hopefully if we have time, we'll go over some final conclusions and questions and answers, which of course you can do right now or via the Twitter account. So in the beginning, well, design patterns. Did they just appear overnight? Where did they come from? Well, in fact, design patterns have a long history starting way back before computing in architecture. That's the construction type of architecture. But it wasn't really until the Goff wrote their seminal book, Design Patterns, that the concept of design patterns was cemented in the world of software development. The book introduces a list of design patterns categorized under three titles: creational, behavioral, and structural. Design patterns are solutions to problems already solved. They represent the collective wisdom of developers and provide us with a common vocabulary. By implementing solutions that are proven to work, we avoid reinventing the wheel and can focus our efforts on solving problems otherwise we would face in our development of our applications. However, we need to take care not to overuse design patterns. Unnecessary use of patterns tends to overcomplicate code, making it hard to maintain, and a poor design pattern knowledge leads to the inappropriate implementation of patterns to problems that we're not meant to design, that we're not meant to solve. So it is very much a case that if the only tool you have is a hammer, then you will see every problem as a nail. So, after the Goff published their book, there was a talk at Java 1 2000 about prototyping patterns for the Java J2 EE platform. This talk became a success, and the speakers published the talk as a book. The Goff book describes a range of patterns, not all common in enterprise Java, but those that are common are baked into the API of the platform. So instead of having to implement them yourself, the platform has them already to use out of the box. So the Java EE programming model has simplified substantially since the J2 EE days. Annotations have replaced the XML description files. Convention over configuration have replaced the tedious manual configuration, and dependency injection hides the creation and lookup of resources. Resources are created and injected at injection points marked by annotations such as @inject. All you need is a POJO that meets all of the conditions of the managed beans specification JSR 299, and depending on the annotations used, it will become an EJB, servlet, singleton, or RESTful web service. The object is injected by the container and is defined by type. However, using an interface as a type can confuse the container. If there is more than one concrete implementation, it doesn't know which object to inject. This confusion can be resolved by the use of a qualifier annotation that marks the concrete implementation you want to implement. We will see how this annotation is used with producer and in the implementation of the factory pattern. Beans are or objects that you want to inject that do not conform to JSR 299, use the producer annotation to make them injectable. Okay, let's have a look at our first pattern. The Singleton pattern is one of the most well-known design patterns and is used extensively by frameworks, pool managers and loggers. If you read the Goff book, it is about having a single instance of an object in the JVM that is only ever instantiated once within the life cycle of the application. Once created, it is not normally destroyed until the application terminates. Why do you need this? Well, the Goff motivation was that heavyweight objects that are expensive are created by the Singleton. If you have read any further in the Goff book, implementing the Singleton pattern is quite non-trivial. You have to start with some pretty unnatural constructs like private constructors, double locking, and the like, and in the end you still don't get thread safety. You need to think about thread safety as it's the single instance being shared across the JVM and across multiple threads. Java EE offers an elegant way to easily implement the Singleton pattern. Okay, so the creation of the Singleton pattern is done by the container, and the container knows to create only one instance because the class is annotated with the @singleton stereotype annotation. By default, this object is read-locked. Access to it is serialized, so you don't have to worry about thread safety at all. So if two threads attempt to access the instance, they will be forced into serialized access. The container creates an instance of a logger class and will inject the same instance wherever it finds an injection point. Injection points are annotated @inject. Let's get to the expensive construction part. Remember, this was one of the principal motivators of the design pattern and why you would want to have the Singleton in the first place. We do this by adding the @postConstruct annotation to the method that constructs the object. This is invoked after construction of the Singleton bean itself. Well, by default, the Singleton bean is instantiated lazily. It won't be created until first use. Normally, this is sufficient for most use case scenarios. However, you may want the Singleton bean to perform application startup tasks, in which case you must annotate the bean @startup. Something that is not elegantly available in the classical implementation of this pattern. The container must ensure that the bean is instantiated before it delivers client requests. Now, the instantiation of your bean may depend on the instantiation of other beans. We can specify this by adding this depends on annotation. Here, the instantiation of our Singleton bean is dependent on the successful instantiation of the connection bean, of the database connection bean. Okay, so already we have seen how the Java EE implementation of the Singleton pattern is markedly different to the classical implementation and requires substantially less code to achieve the same results. You have been given more control over when the bean is instantiated, either at application startup or on first use, and you can specify its dependencies on other beans' successful instantiation. Now, these new features enhance the behavior and performance of the Singleton bean. But we can go further. Now let's look at how Java EE gives us even greater control over the behavior of our pattern. Remember that I mentioned that the Singleton bean is thread safe by default, as concurrency is managed by the container. Well, Java EE offers two types of concurrency management: container bean management and bean managed concurrency. By default, the container manages the concurrency, removing the need to implement the usual concurrency solutions. However, we are given the option to manage it ourselves by choosing bean managed concurrency. Add the annotation concurrency management bean type to the class definition. We still need to be careful with method access as our bean is exposed to a concurrent environment. Two lock types control access to the bean's business methods: write and read. Methods annotated write lock to other beans while being invoked. Beans methods that affect change will be annotated this way. Methods annotated read allow concurrent access. In this code snippet, a call to the getMessage method will be forced to wait until the addMessage method completes. This may result in a concurrent access timeout exception if the addMessage method does not complete within a specified time period. Now the time period can be configured with an annotation either at the class level or at the method level. Okay, so what's good about this pattern? Well, as we have seen, it enhances the behavior of the pattern by using some very specialized annotations. These annotations specify how the bean can be start up. It can either be started up lazily or eagerly. We are given fine-grained control over concurrency and access timeout. And also, this all leads to us having substantially less boilerplate code, and this can only be a good thing. However, what's bad about this? Well, overuse can cause problems, as is the case with overuse of any patterns. Lazily loading causes delays in satisfying client requests. However, eagerly loading causes memory problems if you are occupying memory space that is not ever used. So what's ugly? Well, the design pattern typically is considered an anti-pattern. However, I would argue that there are some niche cases where it is actually very beneficial to use a singleton pattern. But in any case, you may find it's a smarter idea to use a stateless session bean. So let's move on to our next pattern. The factory pattern is a creational design pattern whose intent is to provide an interface for creating families of related or dependent objects without specifying their concrete class. The creational logic is encapsulated within the factory, which either provides a method for its creation or delegates the creation of the object to a subclass. The client is not aware of the different implementations of the interface or class. The client only needs to know the factory to use to get an instance of one of the implementations of the interface. Clients are decoupled from the creation of the object. Often the factory is implemented as a singleton or a static class, as only one instance of the factory is required. This centralizes the object creation. Now in Java EE, we can take advantage of the CDI framework to create objects without knowing the details of their creation. The decoupling occurs as a result of the way Java EE implements inversion of control. The most important benefits this convey is the decoupling of high-level classes from low-level classes. This decoupling allows the implementation of the concrete class to change without affecting the client, reducing coupling and increasing flexibility. The CDI framework itself is an implementation of the factory pattern. The container creates the qualifying objects during application startup and injects it into an injection point that matches the injection criteria. The client does not need to know anything about the concrete implementation of the object, nor even the name of the concrete class is known to the client. So here the container creates an instance of the coffee machine concrete class. It is selected based on the interface drinks machine and injected wherever the container finds a qualifying injection point. This is the simplest way to use the CDI implementation of the factory pattern. However, it's not the most flexible. What happens if we have more than one concrete implementation of the drinks machine interface? Which implementation should we inject? Soft drinks machine or coffee machine? The container doesn't know, and so deployment will fail with an ambiguous dependency error. So how does the container distinguish between concrete implementations? Java EE gives us a new tool, qualifiers. So qualifiers are custom annotations that mark the concrete classes and the point where you want the container to inject the object. We create one qualifier named soft drink. This will annotate the soft drinks machine concrete class, and coffee will annotate the coffee machine class. Here the @target annotation restricts where we can use these qualifiers to mark injection points. In this case on method and field injection points. The annotation with retention policy runtime ensures that the annotations are available to the JVM through runtime. The possible values for target are type, method, field, and parameter. So, two concrete implementations of the drinks machine interface are annotated appropriately. The coffee machine class is annotated @coffee, while the soft drinks machine class is annotated soft drinks. Now you annotate the injection points. Use the qualifier soft drinks to denote where you want the container to be injected, the soft drinks machine class, and the qualifier coffee, where you want the container to inject the coffee drink machine. Now we have made it clear to the container where our concrete implementation should inject, and deployment will succeed. Now we have seen how Java EE CDI framework hides the concrete implementation of an object and allows the creation to be decoupled from its use. We have seen how qualifiers are used to select the required implementation without the need to know anything about the object's creation. It is important to remember that the CDI framework will only instantiate POJOs that meet all of the conditions of the managed bean specification JSR 299. But what if the object you want to inject doesn't? Does that mean we cannot take advantage of the CDI framework's injection capabilities for classes that don't comply? No, it doesn't. Java EE provides us with a solution. Let's dive deeper and look at how we can use the CDI framework to inject any class of any type into an injection point. Java EE has a feature called producer methods. These methods provide a way to instantiate and therefore make available for injection objects that don't conform to the managed bean specifications, such as objects which require a constructor parameter for proper instantiation, objects whose value might change at runtime, and whose creation requires some customized initialization can also be produced, ready for injection via a producer method. So let's have a look at a producer method which produces a list populated with book objects. A list of book objects will be injected into the injection point annotated library. We can even use qualifiers to specify which list of books we want to inject. Here we're specifying a history qualifier, and only books that are produced with the qualifier history will be injected at the injection point here, where we qualify it as history. Also, an important element, an important part of the producer method is its scope. This will determine where the method is evoked and for how long the object it produces will live. By default, the producer method scope is dependent scoped. This means that it has the same scope as its client. We can extend this example further by giving it a wider scope. If we annotate the producer method request scoped, it will invoke only once for each HTTP request in which it participates, lasting for the duration of the request. Possible other scopes are request scoped, session scoped, application scoped, conversation scope, and of course we have dependent scope, which is the default scope. So what's good? Well, it's easy to implement. There's a very limited amount of boilerplate code, in fact virtually no boilerplate code at all, and it works magically. You don't have to be concerned with the construction of the objects. They are constructed by the container and they are made injectable. And you get automatic per class configuration. Each object can have its own specific configurations. And we can use qualifiers to disambiguate or filter the injection of our objects. So what's bad about it? Well, what could be bad about it is if you use the named annotation to specify a particular qualifier. This obviously is not type safe. The solution to this clearly is to use named specific qualifiers such as @history rather than named and passing it to the value history. And what's ugly about it? Well, object creation is hidden, so execution flow could be hard to follow. However, if you're using a modern IDE, you shouldn't have any problems following the execution flow, particularly in IDEs such as IntelliJ. You'll be able to click on an icon in the left hand side menu bar, which will take you through to the creation of the object. So let's have a look at our next object, our next pattern rather. The simple definition of a facade is that it hides the complex logic and provides an interface to the client. Sounds familiar? This is nothing much more than the core part of abstraction, one of the core principles of object orientation. So what is special about this, and why does it deserve its own name and place in the catalogue of design patterns? It's not merely about creating abstraction, but creating a specific type of abstraction in an enterprise system. You will have a layer called the application layer that describes at a high level what that part of your application subsystem actually does. For example, make an order, get a list of products, match given search criteria. It's a high-level API that describes the middle tier of your application. That is really what you are doing with the Façade, describing these high-level abstractions to any user above that level. Perhaps a GUI layer or remote service invocation. They are talking in very simplistic terms to the Façade and telling it, please do this. The underlying code for that would be non-trivial and fairly complex. How do you do this in classic Goth fashion? Really not very difficult at all. They are generally assumed to be stateless objects, often named service or Façade, and you create essentially atomic methods that do a single thing. That is generally how it is implemented in Goth. What does Java EE give you? Well, in this case, Java EE has a specialized annotation. The annotation that I talked about earlier, that is the stateless annotation. It is essentially a marker to denote that this is a Façade and that it is intended to be stateless and to describe atomic operations at the application level. It can do some very useful things. Okay, so it is entirely thread safe. When you access it, it will be thread safe, but it is not a singleton. How it is made thread safe despite not being a singleton, that is beyond the scope of this talk, but essentially it involves some container magic. It is thread safe and stateless. You will never run into thread safety problems. It is by default transactional and is useful for that tier of your application, as you would normally want those high-level use cases to be transactional. Although it includes things like monitoring, management, as well as pooling, and more importantly defining upper thresholds for pool sizes and these sorts of services. It is very useful for defining high-level scalable APIs. Now, it is stateless in terms of what the API expectations are. The implementation may be using things that are stateful. For example, you may have an entity manager that connects to a database. The thread safety is to shield the implementation from any issues with thread safety concerns. Why does it need to be pulled? Well, very simply, this is essentially the backbone of your application. Let's assume that you have a create order method, and let's assume that you get a sudden burst of orders and suddenly you have 10,000 orders to process concurrently. Because this order has an implicit upper bound, you won't run into a thread starvation situation. It will only be processed with the upper bounds of that thread pool, which is typically 10, 15, 100 threads. So what's good? Well, it's very simple, very robust, and it gives you a range of services for free. You don't have to do anything to implement those other than simply annotate your class stateless session. The bad? Well, overuse introduces unnecessary layers. If you don't need it, don't use it. This is an architectural decision. If you want to use it, make sure that it's justifiable within the structure of your application. It's not obligatory to use it, but nevertheless, it gives you some very useful functionality. And what's ugly? Well, there isn't one. It's a very simple annotation that provides very useful functionality. Okay, so let's move on and have a look at our next pattern. The decorator pattern is one of Goth's structural patterns and dynamically adds logic to an object at runtime. So instead of inheritance, the decorator adds functionality at runtime, and it often introduces very large amount of functionality and is very, very flexible. Now, the classical implementation requires that both the decorator and the target object must implement the same interface. And the decorator wraps the target object and adds its own behavior. This can be very, very powerful. Okay, so let's have a look at an example. Okay, so what we can do, we can add the decorator annotation to mark the class that will be performing the decorating task, and the delegate and any annotation to the target class. This is where the object to be decorated will be injected into the decorator class. As you can see here, we're creating a price discount decorator. It's implementing the product interface, and we want to discount our product by a certain percentage. So to set this up, we add these annotations to our class, identifying this class using a decorator annotation as this is the decorator, and identifying that any product object that exists within the system should be injected here within this product Any product object within the system will be injected here where it says inject any delegate. Okay, so now we need to add a priority. Now we define the order in which this decorator is to be applied. We do this by setting the interpreter priority. Note that in CDI 1.1 and below, the order of the decorators are defined in the bean.xml. This is the only pattern that requires any XML configuration. Now, whenever the generate label method is called on the target object, this method is called first, then the call is delegated to the target object's generate label method. Okay, and also we can further refine the objects that are subject to decoration by defining any number of qualifiers, and decorator will be bound to only those beans with the same qualifier. So what's good about this? Well, it's very easy to change behavior without breaking legacy code. And it's simply a matter of extending the same interface and adding a number of annotations. What's bad about this? Well, not a lot, only that in CDI 1.1 you need to use XML configurations to define the order in which the decorators are executed if you have more than one decorator. And what's ugly? Well, again, overuse will introduce execution flows which are hard to follow, but with a good IDE you'll be able to identify where the decorator is by looking at marks shown in the left-hand column, particularly in IntelliJ. That's what you'll see. So let's have a look at another pattern, or the observer pattern. Okay, well, it's a little difficult to understand why it is needed in the first place, and it goes down to the basic fundamental requirements of OO systems, which is to pass a message from one object to another, telling the object to do something as a result of a state change and another object. But the big difference here versus simply invoking a method on a dependent object is that you care about decoupling in one way or another. Perhaps you have an event for which you want to trigger multiple observers, multiple endpoints that react to that particular endpoint because you want some loose coupling, because you want to change which observer actually gets triggered at runtime. Well, this is the original reason you need the observer pattern. Now, the way you implement the observer pattern is sort of antithetical to the original goals of the observer. The Goff way is to implement the interface on a bunch of objects. Then on the listener, you have to register the concrete implementations of each of those instances. It's a bit self-defeating if the goal is to create loosely coupled systems. How does Java EE solve this? It does it in a much more loosely coupled fashion. Okay, so the first thing you need to do is to define an events class. Here we define a class called method event, and within this method event we'd simply define a message as a string message. It's a very simple events class. And here we are, we return a message when the getMessage method is called. Okay, then we have a stateless bean that is listening for events of type message event. When it hears such an event, it calls the message event fire method and gives it a payload that the observer is expecting. In this case, it is a welcome message. Now all dependents are notified. The observer has a method with its expected payload, which is marked with the observes annotation. This says observe for any events that match the payload type of the message, in this case message event. You can also use qualifiers here to filter events. For example, you can qualify the observes annotation by using a custom qualifier. When you fire it, you can statically provide the qualifier at the event injection point and also in the observer method parameter. By default, events are synchronous. However, in CDI 2.2, they are introducing asynchronous processing of events. So, for example, a typical use case might be, well, imagine that you have a significant events in your application that you need multiple endpoints to react upon, and they are not important enough to put in messaging middleware, perhaps a system warning. This lightweight approach is perfect for that situation. So how about transactions? Well, events don't have much to do with transactions. The only place they interact is that you can have an observer that listens on the transaction so that you can get callback saying that a transaction got committed or rolled back. So what's good? Well, it's very easy to implement. There's virtually no boilerplate code. Substantially less work is required to implement them compared to, say, JMS, for example. The container does pretty much most of the heavy lifting. It's a lightweight solution to a problem. What's bad? Well, again, execution flow could be confusing. However, if you are using an IDE, that will certainly help you identify where the observers and listeners are. And what's ugly? Well, nothing. It's actually quite a beautiful pattern and very well implemented. So that's it for today. So what are our final conclusions? Well, as you can see, the implementation of design patterns has been made substantially simpler than before. There is so much less boilerplate code, and by using annotations we have been given much greater control over the actual construction of our pattern and of the way it behaves. Our behavior now is controlled through very simple annotations, and we have access to behavior that before we didn't have. We can start up our singletons very simply, either at startup or on first use, for example, and we can control concurrency very easily. For example, with session beans, we are given a great deal of functionality for free. Pooling, for example, is available simply by adding a sessionless annotation to our class. So there is a great deal of benefit that we can derive from this new way of creating design patterns. And with very simple use of annotations, we can focus our attention on resolving the actual problems that we tend to face day to day, rather than worrying about reproducing boilerplate code. Okay, so if you have any questions and answers, by all means give me a note. Contact me via Twitter if you want to. So that's it. Thank you very much for listening. I hope this has been useful, and I hope to hear from you all again very soon. Take care.